Somebody should remind us where we got to the last time. Rejoice.
Yes, sir. We are talking about the disadvantages of Arrhenius acids and base.
Okay, so we look at equations. Did we look at equations to illustrate Arrhenius concept? I think we did that. We did all of this. Okay, I talk about monoprotic and polyprotic acids. What's the difference between monoprotic and polyprotic acids? Monoprotic and polyprotic acids. I remember I spoke about it. Rejoice, you alone cannot be raising up your hand. You alone cannot be talking. You can be raising up your hand, but let me call someone else. Rosalind, Sedinam. Okay, it doesn't look like Rosalind has joined the class yet. Jasper Kuma, can you hear me?
Say.
Is that Rosalind or Jasper?
Say, please, it's Jasper.
Okay, what's the difference? What's the main difference between monoprotic and polyprotic acids?
Say, please, the polyprotic acids are acids that are capable of ionizing more than one H plus ion per molecule. But the monoprotic acids, they are capable of they are capable of ionizing more than one H plus ion per molecule.
Excellent, excellent. That's the major difference. Monoprotic, they ionize only one H plus per molecule, and then the polyprotic, they ionize two. They ionize more than one. Ionize more than one. And I said under the polyprotic, we have diprotic, meaning they ionize two. Then we have triprotic, they ionize three, and so on and so forth. Okay. The last time I promised giving you an assignment, but I never did, but I'll do that right after this class. I also promised giving you the notes, putting the slides over there for you to go through and fill in the spaces. I haven't done that, but trust me, I'll do that tonight. I'll get some time tonight and give you an assignment, and then also put the note over there. Okay, so and you shouldn't just be able to define them, but you should be able to give examples. That's important. And also not just give examples, but be able to write chemical equations to show how they ionize only one H plus for monoprotic, and how they ionize two H plus ions for diprotic, and how they ionize three H plus ions for triprotic, and so on and so forth. You should be able to write equations to depict that. Then we look at the bases, monoprotic and polyprotic bases. We look at all of that. And then I think this is where we stop also. This was the last slide I showed. And I said in the last sentence, the last paragraph where I said, however, no, the last two paragraphs, that the one that starts by the Arrhenius theory is simple and useful. It explains many properties and reactions of acids and bases. For instance, mixing hydrochloric acid with sodium hydroxide results in a neutral solution containing stable salt. However, the Arrhenius theory is not without flaws. There are many well-known bases such as ammonia that do not contain the hydroxide ion. Furthermore, acid-base reactions are observed in solutions that do not contain water. To resolve this, problems. There's a more advanced acid-base theory. So I said in these last two paragraphs, I have basically hinted on some of the weaknesses and then the strengths, some of the strengths and the weaknesses of the Arrhenius theory. But don't worry, when we finish all of this, the three people's definition, we'll look at differences between each one of them. We'll take Arrhenius against Bronsted-Lowry, and then their differences also give you a hint as to their strengths and their weaknesses. So we'll come back and discuss the strengths of each of the theories and then the weaknesses of each of the theories, much more into details. For now, let me continue and talk about the Bronsted-Lowry theory. Bronsted-Lowry theory. But before I do that, I will need you to, I want to show you a short video. I don't know whether it will work, a very short video. I think it's about 9 minutes or so, basically encompassing everything you need to know about the Bronsted-Lowry theory. Then after that, I'll just talk briefly about some few aspects of it. So let me try this and see if it works. If it works, then you pay attention and just listen.
Two important theories have been developed to explain the properties of acids, bases, and salts. These are the Arrhenius theory and the Bronsted-Lowry theory. Here, we'll look at the Bronsted-Lowry theory. This theory of acids was proposed independently in 1923 by two people, Johann Nicholas Bronsted, a Danish chemist, and Thomas Martin Lowry, an English chemist. We'll introduce the main points of this theory. Before we do that, just a quick word here about a hydrogen atom. Its atomic number is 1, so it has 1 proton. A neutral hydrogen atom also has 1 electron. It is known that over 99.98% of the hydrogen atoms on Earth contain no neutrons. So we'll state here that a hydrogen atom has no neutrons, which is nearly always the case. If 1 electron is removed from a hydrogen atom, it forms an H+ ion. Here's the equation showing that. A neutral H atom has 1 proton and 1 electron. So removing an electron will leave a charge of positive 1, 1 proton, and 0 electrons. So an H+ ion contains no electrons, no neutrons, and 1 proton. Therefore, an H+ ion is the same thing as 1 proton. Or we can say that H+ equals 1 proton. We use the terms H+ ion and proton interchangeably in Chemistry 12. According to the Bronsted-Lowry theory, an acid is any species that donates a proton or H+ ion to another species. Let's look at an example of this. Let's start with a molecule of hydrogen chloride, HCl, and a molecule of water, H2O. Here are the Lewis structures for these molecules. HCl is a polar molecule. There is a partial negative charge on the chlorine atom and a partial positive charge on the hydrogen atom, shown by the delta minus and delta plus. The water molecule is also polar. The oxygen atom has a partial negative charge, and each hydrogen atom has a partial positive charge. The negative charge on the oxygen pulls the partially positive hydrogen atom away from the chlorine. The hydrogen leaves its shared electron with the chlorine atom. The chlorine atom has gained an electron, so it acquires a negative charge and becomes a Cl- ion. The hydrogen atom lost an electron, so it acquires a positive charge, forming an H+ ion, which is also called a proton. The proton moves to the water molecule and attaches to one of the lone pairs. Instead of staying with the hydrogen atom, the positive charge is considered as the charge of the whole ion. So we'll move it over here. There are now 3 H atoms attached to one O, So the formula is H3O instead of H2O. We'll draw square brackets around the H3O because it's an ion, and write the positive charge here in the formula. Chemists call the H3O plus ion the hydronium ion. So we can summarize the whole process here. We started with a molecule of HCl, and we added a molecule of water, which gave us an H3O plus, or hydronium ion, plus a Cl minus, or chloride ion. We can now write an equation to show this process. We write HCl gas plus H2O liquid forms H3O plus aqueous plus Cl minus aqueous. We can also represent the process like this. This shows an H plus ion, or proton, is being transferred from the HCl molecule to the water molecule. So this is called a proton transfer. H2O has gained one proton, so it forms an H3O plus ion. HCl has lost one proton, or H plus ion, so it forms a Cl minus ion. Because the HCl is losing or donating a proton, according to the Bronsted-Lowry theory, it is called an acid. To indicate this, we often call it a Bronsted-Lowry acid, or Bronsted acid for short. According to the Bronsted-Lowry theory, a base is defined as any species that gains or accepts a proton, or H plus ion, from another species. Because the H2O is gaining or accepting a proton, it can be defined as a Bronsted-Lowry base, or Bronsted base for short. So in this reaction, HCl is an acid and water is a base. Because the reactants HCl and H2O are not ions, but the products H3O plus and Cl minus are ions, we call this process the ionization of HCl. Here's a question. We're asked to write the equations for the ionization of the following acids when they're added to water, and to identify the acids and bases on the reactant side. We'll start the first reaction by adding liquid water as the other reactant. The formula for this compound starts with an H, so we assume it acts as an acid, and we'll label it as an acid. So the other reactant, water, must act as a base in this case. Now an acid is a proton donor, and a base is a proton acceptor. So that means a proton, or H plus ion, will be transferred from the acid HNO3 to the base H2O. So this means that water will gain an H plus, which is one H and one positive charge. Adding an H and one positive charge to water gives us H3O plus, the hydronium ion. The acid HNO3 has lost one H plus, which means it has lost one H and one positive charge. We remove the H atom from HNO3, giving us NO3. And taking away one positive charge is the same as adding one negative charge. So we have NO3 minus, the nitrate ion. Both of the new ions formed are aqueous. So this is the equation for the ionization of HNO3. HNO3 is the acid on the left side, and water is the base on the left side. Now we'll see what we get if we add HCN to water. Because HCN starts with H, we'll treat it as an acid, and H2O is a base. So there will be a proton transfer from HCN to H2O. The H2O will gain a proton, or H plus, and form H3O plus, or hydronium. And the HCN will lose a proton, or H plus, and form Cn minus. So this is the equation for the ionization of HCN. HCN is the acid on the left, and water is the base. A double arrow is used here because the ionization of HCN does not go to completion. In a solution of HCN, only a few molecules are ionized. You'll be shown how you can tell whether to use a single or double arrow later in the course. Now let's consider this reaction. Again, the double arrow here, this tells us that this reaction does not go to completion. Instead, an equilibrium exists here. We see that the NH3 has been converted to NH4+. In doing so, it gains one H and one positive charge. Therefore, it gains one H+, or one proton. Because it gains a proton in this case, the NH3 is classified as a base. Looking at water, we see it has been converted to OH-. OH- has one less H and one less positive than H2O. Therefore, it has one less H plus than H2O. Therefore, when H2O converts to OH-, it loses an H plus or proton. For that reason, we identify H2O as an acid in this case. Now we'll look at the previous reaction with water. HNO3 reacts with water. In this reaction, water acted as a base. So we can now see that depending on what it's reacting with, water can play the role of an acid or the role of a base. Such a species is said to be antiprotic. An antiprotic species is one that can act either as an acid or as a base, depending on what it's reacting with. Water is one antiprotic substance. There are many more, as we shall see later in this unit. Monoprotic, diprotic, triprotic, and polyprotic acids. Consider these two acids, HCl and HNO3. Both of these are able to lose one proton only. An acid that has one proton available to donate is called a monoprotic acid. So both HCl and HNO3 are monoprotic acids. Now consider this acid, H2SO4. It's called sulfuric acid. Notice it has two H atoms at the beginning of the formula. Acids that have two protons they can donate are said to be diprotic. So H2SO4 is a diprotic acid. However, when diprotic acids like H2SO4 are added to water, they do not lose both of their protons at once. They do it in steps, losing one proton at a time. In the first step of the reaction of H2SO4 and water, the H2SO4 loses one proton to water, so the water is converted to H3O plus or hydronium. Because the H2SO4 is losing an H plus, it means it's losing one H atom and one positive charge. This gives us HSO4 with a minus charge. HSO4 minus is called a hydrogen sulfate or bisulfate ion. Notice that HSO4 minus has one hydrogen it can lose. So in the second step of the ionization of sulfuric acid, the HSO4 minus will react with water and donate its proton to water, which would produce another hydronium ion. The HSO4 minus loses a proton, so it loses one hydrogen and one positive charge. So it will be left as SO4. And losing one positive charge will cause its charge to go down one, from -1 to -2, or 2 minus. The product SO4 2 minus, or sulfate ion, does not have any hydrogens to donate. So this is the last step in the ionization of sulfuric acid. The double arrow here implies that there is an equilibrium. This reaction does not go to completion. Whereas in the first step of the ionization of sulfuric acid, there is a single arrow, which means this step goes to completion. 100% of the sulfuric acid is converted to hydronium and hydrogen sulfate ions. Now we'll look at phosphoric acid. We see that it has 3 H's at the front of its formula, which means it has 3 protons it can lose. For that reason, phosphoric acid is called a triprotic acid. When it's combined with water, it doesn't lose all 3 protons at once, just one at a time. In the first step, 1 proton is transferred to a water molecule, so it produces 1 hydronium ion. Because it loses 1 H and 1 positive charge, the other product would have 2 H's and a charge of -1. H2PO4- is called the dihydrogen phosphate ion. We see it still has 2 protons it can donate. In the second step, the H2PO4- ion loses one of its protons to water. So it produces another hydronium ion. And since this loses 1 H and 1 positive charge, the other product would be HPO4 2-. This product is called a monohydrogen phosphate ion. We can see that it has 1 proton available to donate. So in the last step, the HPO4 2- donates a single proton to water, producing another hydronium ion. And because it loses 1 H and 1 positive charge, the final ion that it forms is just PO4 3-. This is simply called the phosphate ion. Polyprotic acid is just a general term for any acid that can donate more than 1 proton. Examples could be carbonic acid, which is diprotic, phosphoric acid, which is triprotic, and pyrophosphoric acid, which has 4 protons it can donate.
Video. I guess the latter part of the video talk about what I even talked about the last time we did this, the Arrhenius concept. It talk about the monoprotic and then the polyprotic acids. It talk about that. It talk about how the ionization is done. I said that the last time, that the sulfuric acid, the phosphoric acid, they don't lose all the 2 hydrogens or the 3 hydrogens, you know, at the same time. They don't, ionization is not a one-time ionization. It's a gradual process. 1 hydrogen is lost per time, and so on and so forth. That's not where my focus is. My focus is the earlier part of the video that talk about the Bronsted-Lowry concept. So basically, I think my work has been done by that video. If anybody has any question, let the person ask. But I will show you some few slides, and then talk a bit about some few things. But the video has obviously, you know, okay. All right, this is what I wanted to do. Okay, so as you heard in the video, you see that the concept is Bronsted-Lowry theory. It's also called the proton theory of acids and bases. I want you to take note of that. The Bronsted-Lowry theory is also called the proton theory of acids and bases. And then it was introduced in 1923 by 2 chemists, a Danish chemist, Johannes Nicolaus Bronsted, and the English chemist, people from England, English chemist Thomas Martin Lowry. Basically, the 2 of them, you know, that the theory is actually named after them because of the works they both did. They did their work independently, though. It's not as if they collaborated. What it means is that they all work separately, but they realize that all of them, you know, have the same results. They produce the same outcome about what they want to study about acids and bases. So it was put together and named Bronsted-Lowry theory because they were all saying the same thing about acids and bases. After Arrhenius theory was found to be deceptive, no, not deceptive, to be deficient, not deceptive. Deceptive means deceit. Okay, the theory was found to be deficient in some areas because, like I told you, if you go strictly by Arrhenius theory, then NH3 ammonia cannot be considered as a base because he said the compound that you call a base must contain OH in them. So clearly, ammonia will not be a base according to Arrhenius. So people like Bronsted and Lowry look at that theory and said, no, that theory is a bit defective. It's a bit, you know, deficient. There's something else they can do, you know, about acids and bases that will encompass, that will be broader than what Arrhenius said. But you know, what they rather did, these 2 people, they worsened the case completely. So we'll look at their, you know, the weaknesses of their theories, their theory as well. For instance, water. Okay, they said that an acid is a proton donor. Once you can donate a proton, then you saw in the video, proton is likened to H+. That's a proton. Anytime we say proton, it's H+. The 2 words are used interchangeably. What they said is that once you can donate a proton, you are an acid. So an acid is a proton donor. And once you can receive a proton, you are a base. So a base is a proton acceptor. Now, that is dangerous because their definition, like you saw, can make even a base like ammonia an acid. Their definition can make even a neutral substance like water an acid or a base. It's just a matter of writing equation to show water donating a proton to something else or water accepting a proton from something else. Then it is either an acid or a base. Now, if you look at the dissociation of the diprotic acids and then the polyprotic acids, okay, let me go back and show you, because even under alkenos, we look at that. Good. You can see your slides now. This is an example of a triprotic acid, the H3PO4. Now, if you look at their dissociation, yes, and I agree with the video. Many times when we are doing this, we don't really show, we don't bring the, we don't write the right arrows. We don't bring in the right arrows to depict that because we are not really concerned about equilibrium. But some of these reactions are actually reversible, especially for weak acids like H3PO4. H3PO4 is a weak acid. Later on, you get to know which acids are weak and which acids are strong. In the whole of the chemistry, there are only about 7 strong acids. Only 7. They are the strong acids. All other acids are weak. I'll let you know that, pretty soon. But H3PO4 is a weak acid. Okay? For weak acids, their dissociation is not complete. They dissociate, we say they dissociate partially. So normally there's an equilibrium between the products that are formed and then the reactants. As the reactants are combining to form the products are also combining to form back, the reactants. So, you need to have that equilibrium sign. At a point in the reaction, equilibrium is reached. Okay? And I'm sure you remember from your, chemical kinematics that equilibrium is reached in a chemical reaction when the rate of the forward reaction is equal to the rate of the backward reaction. That's when equilibrium is reached. And it happens only in reversible reactions. The reaction has to be reversible first before equilibrium can happen. It doesn't happen in irreversible reactions, no. So the point I want to make is that if you look at these 3 reactions, look, let me annotate so that you can see. Yeah, I guess can do that. Excellent. So in the first reaction, you see H3PO4, the phosphoric acid donates a proton to water, okay, and then it becomes H3O plus. That's what we call the hydrozonium ion. Now in the video, it was also called the hydronium ion. It's the same thing. It is either hydrozonium or the hydronium ion. It's the same thing. The video used the hydronium ion, so don't get confused. Now, when the H3PO4 donates the proton to water, look at what is left. The H3PO4 is left with H2PO. Oh, it's supposed to be, yeah, H2PO minus. That's right. H2PO4 minus. That's what is left. Now, in the second reaction, the H2PO4 minus also donates a proton to water. Now, according to Lowry, this thing, H2PO4, is an acid. H2PO4 minus, something that is an ion, an anion, can be considered as an acid. But in reality, in the chemistry lab, we don't have these anions, okay, behaving as acid. They are not acids. We don't have these things as real acids. Yes, we have this one. We have the phosphoric acid as a real acid in the chemistry laboratory, and it fits Lowry's definition. When it donates a proton to water, it acts as an acid. That's fine. But if you look at their dissociation to the end, this stage where you have the H2PO4 minus also have to donate a proton to water, meaning that the H2PO4 will then act as an acid because it will also donate a proton to water, making it an acid, according to Lowry, and that's dangerous. Okay, so basically, that is what these 2 people said. Let me go back and then we'll look at that you know. So the year is very important, especially for my friends who are in the National Science and Maths Quiz team, 1923, and the names of the people who did that. Later on, I will need you to go and do a bit more research on these two people. You know how we do it. When they were born, when they died, and some of their major contributions to the field of chemistry or the field of science. Okay. In your WASI examination, nobody will ask you that when was Thomas Martin Lowry, born. No, nobody will ask you that. But in National Science and Maths Quiz, clearly, those are things that can come in riddles, or they help you. They give you clues as to who they are referring to. So, all right. So I spoke about this. Okay, this is again another repetition of the first slide. We just saw T.M. Lowry and then a J.N. Bronsted, Johannes Nicolaus Bronsted, briefly J.N. What did they say? This is the definition. According to Bronsted-Lowry theory, an acid is a proton donor. It's as simple as that. That's the definition of an acid. A base is a proton acceptor. Acids that can donate only one proton are monoprotic, and acids that can donate, more than one proton are polyprotic. We did that earlier on. Now, these are some equations. You saw some of these in the video. Let me talk briefly about them. So, in the first equation, HCl donates a proton. In the first equation, HCl donates a proton to water. And then once it donates a proton to water, HCl will be left with Cl minus because the proton is H plus. Once it leaves, you'll be left with Cl minus. And because it has added a proton to water which was originally neutral, it makes water now become H3O plus. That's what we call the hydrozonium ion. Because HCl has donated a proton to water, HCl is the acid, is a Bronsted-Lowry acid. And because water has received a proton, has accepted a proton, water then becomes a Bronsted-Lowry base. Bronsted-Lowry base. Now, if you look at the second reaction, the HCl again donates a proton to ammonia, and then ammonia becomes ammonium. This one with a plus. It becomes a plus because it was neutral. Then H is being added to it. A plus sign is being added to it. H plus is being added to it. It has to become NH4 plus. That's what we call the ammonium ion. Then the HCl, because he has lost one proton, you will be left with Cl minus. So HCl acts as a Bronsted-Lowry acid, and then ammonia is a Bronsted-Lowry base. Now, there is something interesting. If you look at the first reaction over there, if I ask you to write the first equation, if I ask you to write an equation to show HCl acting as an alkenious acid, basically dissociating in water, ionizing in water, it's the same equation you will write. Either you write that, or you write HCl just breaking down into Cl minus plus H plus. We'll look at that earlier. But when you are writing it to show a Bronsted-Lowry acid, you have to add water. That's the easiest way of writing any compound to act as a Bronsted-Lowry acid. Very, very easy. Just add water to the compound and let the compound donate one H, one hydrogen to the water. That's all. You have made that compound to behave as a Bronsted-Lowry acid. So it doesn't matter what compound you are giving. Once it contains H, hydrogen, you can write an equation for it to act as an acid. And the easiest way of doing that is by adding water to it. Then let one hydrogen leave that compound that you've been given to write an equation for. Let one hydrogen leave that compound to water, and then that's all. The compound then acts as an acid. It's as simple as that. You see, and that's the danger with the definition, with these two people's definition. Now, because I can even write an equation to let ammonia, NH3, act as an acid. Right? Ammonia, NH3 plus water. If I want ammonia to act as the acid, and I hope you are writing, one hydrogen will leave the ammonia to water. Then at the product side, you have NH2 minus plus hydrozonium ion. You have NH2 minus, which is really nothing in chemistry. NH2 minus plus hydrozonium ion. Because one hydrogen has left ammonia, which is NH3. The product will then be NH2. Then there will be a minus at the top of that. You see, in that case, I'm making ammonia act as an acid by making it donate a proton to water. But in reality, all of us know ammonia is not an acid. So you see the danger that these two human beings wanted to put us into. Everything can act as an acid, anything at all. Once it contains hydrogen, you can make it behave as an acid, and that's dangerous. You can even look at the third equation. You can even make ammonium ion a radical, ammonium ion a radical, a cation. You can even make it also act as an acid by you see, making it donate a proton. It donates a proton to Cl minus. It donates a proton to Cl minus. Then the Cl minus, after receiving the proton, accepting the proton, then becomes HCl. The minus will go away because you remember proton is plus. Then the ammonium, after losing the proton, you then have ammonia. Now you see this equation is more or less at the reverse of the first equation. Oh, not the first equation. Okay, but you can actually write a reverse of this same equation and let the HCl. Oh, yeah, it's actually the reverse of the top one, the middle one, this one. Okay. In this case, ammonium is acting as the acid. So Bronsted-Lowry theory reactions are actually reversible. Many of them are reversible. A substance is an acid at the reactant site. Okay, if the reaction is going in the forward direction. If the reaction is going in the backward direction, that substance can become a base, and so on and so forth. And it gives rise to a special concept we call conjugate acid-base pair that we'll look at. Conjugate acid-base pair. Conjugate acid-base pair. You can see that in the third write-up I have here. I said, so look at the middle reaction. I said water is not necessary. In this case, hydrochloric acid is still the acid, but ammonia acts as a base. Water is not necessary. And that's one of the strengths of the Bronsted-Lowry theory. Hello, can people hear me?
Yes, sir.
Yes, sir.
Excellent. That's one of the strengths of the Bronsted-Lowry theory. You don't need water to prove that a substance is an acid or a base. Now, in the third reaction, I said the same reaction is happening, but now in the reverse. But what was once an acid is now a base. That's HCl becoming Cl minus. And what was once a base is now an acid. That's ammonia becoming ammonium plus. This concept is called conjugates, conjugate acid-base pair. Need to be explained in more detail later. Okay, these are some few more example. This is actually a neutralization reaction, but this reaction can be simplified as this, just trying to illustrate that neutralization reactions are essentially reaction between a proton, H plus or hydrozonium ion, and the hydroxide ion. All right. So I said the Lowry theory is by far the most. Useful and commonly used definition. For the remainder of general chemistry, you can assume that any acid or base, any acids or bases use the Lowry definition unless stated otherwise. This is very important because for basically the acids that we have, they are acids that conform to the Lowry's definition, acids and bases. The Arrhenius is not sufficient. The Lewis is even worse. The Lewis concept is even worse. Gilbert Newton Lewis is even worse. So this is like in the middle. It embraces the Lowry concept. No, not the Lowry. The Arrhenius concept, and then at the same time having something more than the Arrhenius concept. Because trust me, every acid that is an Arrhenius acid can be a Lowry acid. Every acid that is an Arrhenius acid is also a Lowry acid. So this theory is more enhanced, and many of the acids and bases we consider in chemistry are largely based on this theory. Okay. Now, before we go to the conjugate acid-base pair, I don't know if anybody has any question to ask based on all that I've said, but under this topic, what is important is you giving a compound in an examination, apart from you being asked to define these acids and bases according to this theory. You can also be given any compound at all, and you'll be asked to write an equation. It's about chemical equation. Write an equation to show how that compound acts as a Lowry acid, or how that compound can behave as a Lowry base. And let me repeat this. Any compound that you've been given to write an equation to let it act as a Lowry acid, just add water to the compound. So the compound plus H2O. And then let the compound donate H to the H2O. Then you have hydrozonium ion and the anion of that compound. It's as simple as that. It's as simple as that. Now, that is not to say that you cannot write for any other compound other than water, or you cannot add any other compound other than water, but water is the simplest one. In fact, if I'm given a compound like ammonia, and I'm asked to write an equation for ammonia to behave as an acid, I can as well add ammonia. So ammonia plus ammonia. Then I'll have NH4 plus and then NH2 minus. Okay. But the simplest way of doing that is to add water. Then, if you are asked to write an equation for a compound, showing a compound behaving or acting as a Lowry base, again, the simplest way of doing that is to add water. But in this case, let the proton leave water to that compound, because a base is a proton acceptor. So in that case, let water be the one to donate the proton to that compound. The rest of it is about charges, it's about balancing charges and writing the correct formula. Otherwise, you'll be wrong. Or otherwise, it's something very simple. Okay. For instance, I'll need you to write an equation to show how H2SO4 can act as a bronzoluric acid. H2SO4 acting as a bronzoluric. Rejoice, I see your hand up. Please go on. Rejoice, if you can hear me, please come again. The network is, your voice is breaking.
Sorry.
Yes.
Okay. The H2S4 is I said.
Oh, I think I just lost Rejoice. Okay.
Say.
Yes.
Say the H2. The H2SO4 is a diprotic acid. So you have two equations.
So you
the
give
first one, you have H2SO. Should I give the first one
just
and
give
the
me
second one?
any equation.
Okay. H2SO4 aqueous plus water, which is liquid, giving us hydrozoium ion plus HSO4 minus aqueous.
Okay, that's fine. That's all. That's one equation you can write. And that's correct. Somebody can also decide to write the overall equation. Okay, H2SO4 plus water going to, so in this case, it will be 2 moles of water going to no, that would be wrong. That would be wrong. What you said is right. It's just a proton. So not 2 protons. No, it's just a proton donor. So what you need to write is what Rejoice said. You can write H2SO4 plus water going to 2 moles of hydrozoium ion plus SO4 2 minus. No, that would be wrong. That will be wrong because an acid is a proton donor, not 2 protons. Courage, I see your hand up.
Okay. Sir, please, you see the H2SO4. When we are asked to write the complete dissociation, then can we write the two equations?
Okay, yeah, you can. If you're asked that, you can write the 2 equations. Okay. And then normally what we do is when you write the 2 equations, you see the two equations, the 2 equations add up to give you the overall equation. And the overall equation is H2SO4 plus 2 moles of water going to 2 moles of hydrozoium ion plus SO4 2 minus. That will be the overall equation. But you need to show the breakdown one after the other. And the point I'm making is that the question I asked is write an equation to show how H2SO4 acts as a bronzoluric acid. Just let it donate 1 proton to water. Then you left with H2, you have H3O plus, that's a hydrozoium ion, plus HSO4 minus, like we just said, the bisulfate ion. That's all that you get. If you write the overall equation where it donates the 2 hydrogens at a goal, you are wrong. Because the definition says a proton donor. Alternatively, if you know what you are doing, you can also decide to just write the equation. You can write HSO4 minus, okay, plus water. In that case, it donates the proton, and you have SO4 2 minus now, and then the H3O plus. That is if you are asked to write an equation that shows how HSO4 minus can act as a bronzoluric acid. Okay, I want to give you another example, and I want somebody to try this. I'll mention some name. Agbemo Williams is there. You've been quiet. Carry is also them. I'm giving you a compound, ammonia, NH3. Write an equation to show how ammonia can act as an acid, according to Lowry. Bisa, Nana Kofi.
Yes, sir. Okay, so the question I had was, okay, is NH3 plus H2O going into H3O plus NH2 minus.
Excellent. Excellent. That's all. That's correct. But one thing you need to do is to indicate the states of the species, okay? Aqueous. Normally, all species that are charged, if a species has a charge on it, minus or positive, so it's always in the aqueous state, so you put AQ. Then, of course, water is liquid. Ammonia in this case will also be aqueous, because what I'm asking you to is always the aqueous form. It's not the gaseous one, it's the aqueous form. All right, thank you. Maybe the last one. I said the last one, but the very last one. In this case, I want an equation for ammonia, the same ammonia acting as a base, in this case, Lowry base. Precious, SEM. Jessin, Awaga, Chromil, be ready. And then Frank, Nukunu, you follow in that order. First, Precious, SEM. Agbemo Williams, are you on this page? Are you listening to me? If you can hear me, just unmute yourself and say, yes, sir. Agbemo Williams. Oh, wow. The last time I think very soon I need, almost all of you have muted your videos. I don't think we'll have a problem with that, because we've realized that when you mute your videos, it saves a bit of data as opposed to if it is on. But from time to time, teachers will be demanding that you unmute your video so we can see your faces, because it looks like there are some people, they just come and put the device on, and then when they are admitted that their names are in the class, they leave the phone and then they leave and go and be playing. Can you imagine? Okay, Agbomo Williams just sent a message that he can't hear anything. I guess so. I guess that's why he's not responding. But his audio is connected. I don't know what the problem is. It could be his network. Last I was teaching Form 1 students, there was a guy who, he was actually by the phone. The earpiece was in his ear, and the guy was sleeping. He was far gone. I mentioned his name several times. He didn't respond. I don't know whether he's still alive now. Precious Sam. Okay. How are you, Daniel?
Hello?
Yeah, please go on.
NH3 aqueous plus H2O, that's in the liquid form, going into NH4 plus aqueous plus OH minus aqueous.
Excellent. Excellent. So it's just a matter of making water donate a proton to the water, to the ammonia. That's all. It's as simple as that. Good work. Let's go on because I need to finish this. So I said this, and then I wanted to talk about the next thing, the conjugate, or we call conjugate acid base pair, conjugate acids and bases. Conjugate acids and bases. If you take your past questions, many a times questions under acid base and salt, students are asked to define what is meant by the conjugate acid of a base, or what is meant by the conjugate base of an acid. That's the full pronunciation. But the two are called conjugate acid base pair. Define conjugate acid of a base. That's how it's pronounced. Or define conjugate base of an acid. You see, that's how they are antagonistic to each other. But if you look at the equation that is there, I don't know whether it's clearer on your screen. We've written this equation before where HCl. So you see here, I've actually brought the equilibrium sign where HCl donates a proton. Just a minute, please. If you look at this equation where HCl donates a proton to water, so water is acting as a Bronsted-Lowry base because it is accepting a proton from HCl. HCl is acting as a Bronsted-Lowry acid. That's in the forward reaction. So it gives you H3O plus aqueous plus Cl minus aqueous. Now, in the backward reaction, if you analyze the backward reaction carefully, you see what is happening. It is clear that the Cl minus, okay, in the backward reaction, the Cl minus accepts a proton. The Cl minus accepts, I was trying to annotate. The Cl minus accepts a proton from hydrozonium, and then that gives you a proton is donated from the hydrozonium ion to Cl minus, and then you get back. This then forms the HCl after it accepts a proton from the hydrozonium ion. What does that mean here? It tells us that in the backward reaction, Cl minus is a base because it is accepting a proton. You see that? Now, the hydrozonium ion that donates the proton to Cl minus, it tells us that the hydrozonium ion in the backward reaction is an acid because it's a proton donor. Where did it come from? Where did the hydrozonium ion come from? It came from water accepting a proton from, HCl. And if you remember the video, this was illustrated, very vividly. The hydrozonium ion came from water after accepting a proton from HCl. So in the forward direction, water is the base because it accepts a proton from HCl to form hydrozonium ion. In the backward direction, the hydrozonium ion donates a proton to the Cl minus, and then the hydrozonium ion forms water. After it donates the proton that it gained in the forward reaction, it then forms water. Water and H3O plus, the hydrozonium ion, then become what we call the conjugate acid-base pair, where the hydrozonium ion is a conjugate acid because that's the proton donor. Normally, that's what we write first. We write H3O plus slash H2O. Water then becomes the base. The HCl aqueous and then the chlorine minus aqueous also form a conjugate acid-base pair, where the HCl is a conjugate acid and then the Cl minus is a conjugate base. Now, what do you notice? Let me